thanks so much, Olga, for such a kind introduction, and to all of my associates for giving such interesting and entertaining presentations. It's hard to plan for an event like this. Planning isn't something that I'm all that good at. One of my major theses is that our lives are a matter of trial and error, and we keep presumably repeating successful behaviors and drop out the unsuccessful ones. But I find more often than not that I go back to projects where things didn't work out so well the first time because the sense of closure just isn't there. And so I'm perfectly happy to return to old problems, old methods, and sometimes retool them, re-examine them, and take things from a fresh point of view at that juncture. What I'm going to talk about today is something that's been quite near and dear to me for some time. I took something of a sabbatical from the area of categorization, or at least this brand of categorization, but I've gotten re-inspired, and I think maybe it will be a good object lesson for all of us, that sometimes things unfold slowly as well as quickly, and I think you can arrive at interesting and useful points nonetheless. So let me try to use the clicker thing that it's given everybody else trouble. I suspect I'll have the same trouble, but let me begin. That was a test. So this is Charles Otis Whitman. Most of you don't have a clue who this is. He happens to be a famous figure in the history of American zoology. He's a founding father, they say, of ethology. He studied pigeons for many decades. He owned Martha. This is an important point. Martha was the last living passenger pigeon. That's a different story, not a happy one. But he had a very dim view of pigeons insofar as their intelligence is concerned, despite having worked with them for 50 years. The quotation that I find most enjoyable here is this: "Whatever the pigeon instinct mind contains, it is safe to say that intelligence is hardly more than a grain hidden in bushels of instinct, and one may search more than a day and not find it." Not giving very much cred to our feathered friends, even though they were the subject of his life's work. This is another man with whom we're much more familiar. He too messed about with pigeons. You can see him in a pose that I have never seen before. I found this recently. That is Skinner. He was a founding father of behaviorism. He began studying pigeons in Minnesota in the middle to late 40s. Many of you may know that this work began with a famous project where pigeons were intended to guide missiles, and that's another talk in and of itself. We have much more benign interests in pigeon behavior than that. And at this time, Skinner said this. This is an actual quote. "The pigeon," he said, "is especially good at responding to patterns, and those classes of patterns called concepts." But he never bothered to define what he meant by concepts. And that fell to others who have a close connection to Skinner in the history of behaviorism, Keller and Schoenfeld. They had something to say, I think something profound to say about concepts. So on the left is Fred Keller, on the right is Nat Schoenfeld, and in the middle is a book. Some of us may know that book, but perhaps not so many. Many more should. It was an introductory psychology book called Principles of Psychology. It was an introductory psychology book based on behavioristic principles. And their approach was decidedly special. And I'll make it clear how special. Oh, and by the way, who was Fred Keller? Fred Keller was a classmate of Fred Skinner, the two Freds from Harvard. And they were both devout behaviorists. Skinner ultimately returned to Harvard to teach many generations of behaviorists. Keller quickly went to Columbia, where many other behaviorists were trained, including Nat Schoenfeld. And just in case you think this is completely irrelevant to me, Nat Schoenfeld was a close associate of Elliot Hurst, and he was my PhD advisor. Okay, so why am I speaking about such a moldy oldie as this? Well, Keller and Schoenfeld discussed in some length what it meant to speak about conceptual behavior and concepts in general. And they urged great care in defining this word of concept because they deemed this not a thing. Concepts aren't things that are in your head and grow. They're rather names for kinds of behavior, the things that organisms do. So they said, we do not have concepts any more than we have extinction. Proper analysis, they urged, should instead start with a different question. What type of behavior is it that we call behavior, or conceptual behavior? That is, what do we do that leads us to invent this term? And the answer is quite simple. When a group of objects gets the same response, when they form a class whose members are reacted to similarly, we speak of a concept. The essence of concepts, they said, generalization within and discrimination between classes. That's the essence of concepts. So familiar terms, generalization and discrimination, come to us together and lead to what we would recognize as conceptual behavior. And they gave an example. When some stimuli occasion the response car, whereas other stimuli occasion the response flower, we're seeing conceptual behavior in action. Okay, that's it. That's all there is to it. And from casual observation and theoretical analysis, Keller and Schoenfeld went out a little farther. They suggested that non-human animals may exhibit fundamentally the same conceptual behavior as human beings. Oh, there it went. So they also suggested that this was a fresh opportunity to explore some long-standing questions in the psychology of concepts. First, are humans alone in making and using concepts? And are the roots of human language to be seen in the behavior of animals? Because to some serious extent, language and concepts are bound together. So let's talk just a little bit more history, the relationship between concepts, categories, and words. Well, that's an enduring issue indeed, and it dates back to the 17th century to famous philosophers René Descartes and John Locke. René Descartes said that none of our actions can show that our body is not merely a self-moving machine, except for words or other signs that are relevant to particular objects. He said that the use of words is peculiar to human beings. And most prejudicially, he said, animals do not speak as we do because they have no thoughts. Okay? So they have nothing to talk about. It isn't that they don't have the means of expressing themselves. They simply haven't anything to say because they haven't anything to think about. John Locke argued that the having of general ideas perfectly distinguishes humans from animals. Animals, he said, lack the power of abstracting or making general ideas. And why was he so sure of this? Because animals have no use of words or any other general signs. It's a catch-22, right? There's no way animals are going to get out of this bind, right? They have no thoughts, they don't speak because they have no thoughts. You know, it's hopeless, right? The door is effectively closed. And what I wanted to urge right now is you see that Keller and Schoenfeld, some years later, suggested there may be a way out because conceptual behavior may not need words. So, as to the matter of words and animal research, here are three famous examples, of course. We have Lana operating her keyboard at Georgia State University. We have Kanzi, who started at Georgia State and is now in Des Moines. And we have Washoe, engaged in all interesting, exotic experiments, some would say, in the use of perhaps a language-like behavior. Let's just take for one example, Project Washoe. The gardeners claimed that Washoe and 3 other chimps had passed a vocabulary test for dozens of American Sign Language signs, okay? And you're all familiar with this, so I don't need to rehash it, but it was a pretty important observation, and it excited a good deal of research and even more controversy. Dick Herrnstein went in a different direction. Instead of working with those more human-like species, he worked with pigeons. And he initiated this additional or different approach that followed the thinking of Keller and Schoenfeld and the methods of Skinner, his mentor. As did Skinner, he studied pigeons in an operant conditioning chamber. The specific experiment, the classic that we all know, is in 1964. Herrnstein and Loveland taught pigeons to respond if there was a photograph that contained a person. Sometimes the person was a prominent part of the photograph, sometimes the person was a subtle feature in the photograph. Other photos that were, well, highly varied as well, simply didn't contain people. And if there were a picture of a person in the slide, food would be delivered on some schedule of reinforcement. If there weren't, no food would be delivered. The pigeons were able quite adeptly to learn this discrimination and later generalize with relatively little decrement to new examples. And this, they suggested in their abstract, suggested that the powers of conceptualization can be demonstrated in animals, and animals that were, to use Skinner's own term, lowly, or lower species. We don't use those terms, certainly not here, but he did then. Well, that's the classic in the field, okay? That's the classic in the field. It was, in fact, a groundbreaking study. It attracted a great deal of attention and interest, but in my estimation, it seriously lacked verisimilitude. It had no bearing whatsoever to what we do when we exhibit conceptual behavior. We don't walk around talking about persons and non-persons, trees and non-trees, cars and non-cars. It's utter nonsense. We, as Plato, carve nature at its joints. Our words denote collections of stimuli that cohere and that are readily discriminable from one another. That's what nouns do. And so this was what I was teaching my students back when I started in 1972 and several years thereafter, and honestly got increasingly disenchanted with this as being such a pale replica of what conceptual behavior really is that I decided to do something about it. So we did an experiment. And the experiment that we did, again, used pigeons, put them in Skinner boxes, but we provided them with more interesting stimuli, and stimuli that had, we thought, more similarity to, more resemblance to the kinds of stimuli that we see and categorize on a daily basis. We chose 4 categories because 4 was a pretty nice number. We could array them around a viewing screen, and Homa and many other people in human categorization had used 4 categories for people learning artificial stimuli. So we thought that that was well in line with what was state-of-the-art at that point in time. The categories that we picked were cats and cars and chairs and flowers. At some point in our conversation today, we're going to move to different categories. We couldn't stick with cats for very long because later experiments demanded more examples, and cats just aren't that photogenic. They're just not around. So we had to substitute another species. We picked people. So this was the view of the pigeon box from above. The pigeon would have a viewing screen, and there would be arrayed around the screen 4 different buttons, each in a different color. In these experiments, they stayed in the same location. In later experiments I'll describe, they get randomized. In the old boxes, we had a grain feeder. In the new boxes, we have a pellet dispenser on the back wall. From front on, what the bird sees, it's very easy to do, what the bird sees is the viewing screen, and it is illuminated with a picture. And it's a picture of a cat, a car, a chair, or a flower in this first experiment. Only one of them at a time. The pigeon pecks it many times, 10, 15, 20, 25, 30, depending on the bird and how far we have to advance him before he starts discriminating. And then the corner buttons come on. The buttons come on after the observing response is complete. And then the bird is given 1 chance at a correct response. well, the odds are 25% that it's going to make the correct response. If it does luck out, it gets food right from the outset. But if it makes a mistake, it gets a correction trial. And it keeps getting correction trials until it makes the correct response. That way, every trial ends with the correct association being strengthened, we would believe. And it also involves a form of punishment. The bird has to keep working, re-observing the stimulus and choosing again. So errors delay the next feeding. So it's a kind of punishment that we now realize is an important feature of these experiments. And that's it. Some little details. In the early experiments, we had a slide projector. We had 40 slides, 10 from each category. There was this fixed ratio observing response requirement. And on the completion of that, the buttons would come on for the choice response. We would give food if the bird were correct. We wouldn't give food if the bird were incorrect. We have these correction trials. Come testing time, because we have to test whether the birds have learned something general when we show them new examples of the categories. Come testing time, we either give them only one trial and they're correct or incorrect and that's it. We in the first experiments gave them differential reinforcement then, but it didn't matter because they never saw the slide again. Or, more frequently, we give non-differential reinforcement. They can choose whatever they want and they'll get food and move on. So this was the first experiment that we did. It was published in JEP in 1988. Many other experiments were part of this project, but this is the basic result. You see that the birds start at about 25% correct, which is chance. Over the course of 30 days, they get upwards of 80% correct. Of course, we were impetuous, like Kim's rats. We wanted to know what was going to happen, so we decided we would go ahead and test them. It's pretty clear that if we had kept training them, they would have gotten better still, but that seemed good enough for us at the time. We then showed in a test session old slides, these same ones, and brand new ones from the category. And you see something just utterly characteristic. The birds did generalize to new examples that they'd never before seen, and there was a decrement in accuracy when they saw the new ones. There's nothing strange here. Okay, no spoiler alert is necessary, because you do the experiment with artificial categories in people and you get the same result. Now, you will see soon that this and many other things are parameter dependent, Mike. So the fact of the matter is it's just our first foray, and it was a good one. It suggested that we were on the right road. This, by the way, for those of you who care, was the first experiment. There was no pilot experiment. Sometimes these things work right out of the gate. Not always, but sometimes. So in follow-up studies, over the span of 20-some-odd years, we've looked at a number of variables, how they affect behavior, beginning with Ramesh Bhatt, who did his dissertation in my lab and is now at the University of Kentucky, one of Tom's esteemed colleagues. In later work, we went back at these issues from a modeling standpoint. Fabian Soto, who will be here in Florida International next year as a faculty member. And what I'm going to actually show you coming up is going to show you not necessarily data, but the predictions of the model that effectively capture all of the data that we collected over many, many years. Okay? So first I'm going to describe you this model, which is effectively an amalgamation of Estes stimulus sampling theory and the Rescorla-Wagner model. No offense, Ralph, it still is the state of the art. Hang in there, though. But you'll see that the model does an admirable job in explaining the data that we've collected. And you'll see that the experimental tricks are many and sometimes useful. So the model starts with a pigeon, that's the bird. And if you show the pigeon a picture of a car, you assume that some number of elements is activated. These are hypothetical elements, but something in the brain of the bird is changing for sure. And you show them another car, it's a different color, a different set of elements is activated. Notice the overlap. You show them another car, right, a different color, and you can sort of see the pattern. There are going to be some elements that are specific to individual stimuli, and there are also going to be elements that are characteristic of the category. So on presentation of any stimulus, you have to appreciate there are going to be individual elements and categorical elements. And this is an important part of the yin and yang behind the category learning results that we're going to now show you. Okay? So here's the effect of, that just bumped. So here's the effect of learning model. You already saw real data, so here's some simulated data. And of course, here's the generalization decrement that's typical. So we built into the model the parameters that were very similar to what we used in the first place, and you can see acquisition and incomplete transfer is captured. Now what? Well, in the next model, and we have data to show it, we varied the number of examples per category. So in this case, there were 12 examples for each of the 4 categories. 12 cats, 12 cars, 12 chairs, 12 flowers. And in one group, they saw just 1 cat 12 times, 1 car 12 times, 1 chair 12 times, 1 flower 12 times. So there's no variability. It's just the same stimulus over and over and over and over again. In another group, they see 4 examples per category, right? 4 of each in a session, repeated now 3 times. And finally, there's a group that sees 12 different examples of each of the categories, only 1 time a session. They're repeated across sessions. And what happens? Well, if you look at learning, learning is really, really fast with 1 example per category. It gets slower the more examples per category you add. Perfectly consistent with everything people had ever published before in human categorization. Testing. What happens in testing? Well, here's accuracy to the old stimuli, and you see it's pretty high, from 75 to 85% correct. Look at transfer. For the pigeons, or stat pigeons in this case, real pigeons in other cases, the real pigeons were 27% correct. They knew nothing of any utility whatsoever when you showed them 8 new examples of the categories. No transfer at all. As you increase the number of examples in training, you increase the level of transfer, you decrease the extent of generalization decrement. These data look just like the real data, but for something different, here are the simulations. Okay, so the model is working quite well for accounting for parametric data. Now we can't tell you exactly the form of the function, but maybe someday. Nah, this is painful. So we did another experiment. This experiment was a project that we did because we had a minority student. We got extra money to do it. We got a 35 millimeter camera. We shot 2,500 snapshots. Okay, a lot of snapshots. 2,000, I should say. 500 people, 500 flowers, 500 cars, 500 chairs. And we showed them only 1 time. Okay? So we have a group of pigeons that are trained, and they see them only 1 time each. So this is an ultimate experiment. There's no repetition at all possible. The only way they can learn the concept is if they have memory from what they had learned in prior occasions. And in that case, those birds learned. The data that I'm showing you now come from a second batch of birds asking, is there any effect of repetition at all? If they can learn, does actual repetition help? So in this particular simulation, we included the group that I just described with brand new stimuli. These happen on days 1, 3, 5, 7, 9, and so forth. These happen on 2, 4, 6, 8, 10, 12. They're the repeats. So we have 1 set of slides on odd numbered days that are dumped out and new ones are put in every time. They see new slides every time. And we have another set of slides that is shown on even numbered days. And the result is, of course, they learn even without repetition, but they do better with repetition. So repetition helps. And it's perfectly consistent with the model. And there we go. So we don't need repetition at all. I don't know of anybody else who's done an experiment like this where categories are learned without any opportunity to see the same example again. But it's pretty impressive. The birds, Whitman would be surprised. So now we go to some of our tricks. Okay, this is actually a trick that pays homage to Vern Honig, but Dick Kernstein also included it in one of his experiments. This is a pseudo categorization control. The conclusion that Herrnstein came to was that, in fact, this assiduous training of the birds wasn't necessary. They already had these concepts. All the training did was allow us to see them. And the argument he made was that something in the perceptual dynamics of the bird glues them together. Cars look more like cars than they look like flowers, chairs, or people. And likewise for all the other categories. So how do we actually see what this principle is all about? What kinds of designs can we use? So the pseudo-category task is one of them. So you already know what a real category task is. That's no trick, all right? Cats and cars and chairs and flowers. But this is a pseudo-category. So the pseudo-category, all these blue stimuli, involve 1, 2, 3 flowers, 1, 2, 3 cars, 1, 2, 3 chairs, 1, 2, 3 whatever the other one was. I can't keep track after a while. So the point is that these pseudo-categories are random collections of stimuli. If you try to use the natural groupings, all the A's, like all the cats, for instance, it's going to kill you. You can't do the task. It's exactly orthogonal to the categorization that's being taught. So you have to remember every exemplar. So this, as you think about the model, this cannot capitalize on the category-specific elements. It can only be learned by the individual stimulus elements. If you were a pigeon, you would volunteer to be in the true category group, and you wouldn't want to be in this pseudo-categorization group, because that's a beast, okay? And what happens? This is the simulated data. This is the real categorization task, starting from 25% going up to 75% with these parameters. Here's the pseudo-categorization task. I can tell you with real pigeons on this task, the guys got to about 80% correct on the true category and 44% on the pseudo-category. So the simulation perfectly matches the data the birds generate. Why does this happen? Because something in the perceptual dynamics of the bird binds these stimuli together. Things that look alike are more easily categorized, and you can use that to your advantage in this task, and it's at your disadvantage to use it in the pseudo-category task. Okay? Is that clear? Maybe. Okay. I'm not seeing enough smiling. If you didn't like that one, this one's worse. This is a subcategorization task. This is a unique Iowa invention. In order to do this task, you have to have actually 4 sessions so that all the different stimuli can be seen. And in this particular example, there are going to be cats that are presented in some sessions. Half of the cats will require, let's say, an upper left-hand peck. Half of the cats will require, let's say, a lower right-hand peck. Half of the flowers lower left, half of the flowers upper right. Uh-oh. Now this is kind of a hybrid. You can get 50% correct if you attend to these 2 responses for flowers, but you can't get 100% correct because you've got to memorize them too. So both individual stimulus and categorical information have to be utilized in order to work through this. Well, let's see. And the other sessions are similarly constructed. So the point is that we have shifting arrangements, and it takes 4 sessions for the birds to see everything. As hard as it may be to explain to you, it's not that hard to explain to the pigeons. Let's first look at different categories of responding. Here's correct performance. These are correct identifications, and you see they rise quite systematically. Here are guesses. We have a Markov model that allowed us to estimate the guesses on the part of the pigeons. And those are going down. So learning is, well, they're going up here and they're coming down here. What in the heck is this curve? Those are responses that we can attribute to the birds categorizing, but not yet being able to segregate them into the sets. Right? So the point of this is that the bird, if it sees cars are as more like one another, will make one of these 2 responses, not the other 2, but that won't get them all the way home. And so the one really fascinating detail in the data happened here, because early on, the birds are more likely to categorize the stimuli than they are to identify them. So identification responses lag behind categorization responses, which is what the model expects. Why does the model expect that? Because every time you see a car, any car, category-specific elements are there. But there are 24 different cars. So the individual elements are going to lag behind the categorical learning. It's a feature of the model, and we think of the stimuli themselves. I don't know that anybody else has extracted this kind of evidence out of a categorization study, but it's a pretty cool maneuver. We're really pleased at how this turned out. And the model fits it perfectly. I mean, we didn't get this first. The birds behaved, and then we tried to simulate what they were doing. So despite the similarity of this project to this point to what the gardeners had done, we resisted calling our work a vocabulary test for pigeons. And we actually wrote this in the discussion section. Because the fact is the birds had only learned a small number of categories, number one, and number two, who was going to buy it, right? Who was going to buy that the pigeons really were categorizing? So we were a little bit cautious. Those were the early days of my career. So later efforts have been more ambitious. And we've tried in these later studies to teach a richer vocabulary, a larger number of categories to the birds, to try more closely to approximate the prodigious number of categories that we learn. Washoe had at the time 32 different words. Well, we thought maybe we could get something close. And just to give you a little background on why we might want to do this, the point of all of these experiments, in our estimation, has to do with associative learning and the role, we believe, of associations in word learning. You remember that Keller and Schoenfeld suggested that there was going to be some connection between word learning and the kind of behavioristic analysis they provided. We would speak now more about associations per se. So let's just take a look at some papers that have appeared. So you've got Waxman and Gelman saying that there's something much more than mere association involved in forming words. Well, what that something might be is of interest, and perhaps we'll simulate that sometime too. Boy, this is a killer, and I warned you guys. Another is that there may be something more involved in learning than just associations. Maybe observation is important. Linda Smith suggested that there was nothing wrong with association, you guys just hated behaviorism. So that was something else that has come up in this literature. And more immediately relevant in my hometown, we have colleagues. People who were quite interested in associative learning and the effects of learning on this associative process on word learning in kids. People really study children's word learning. Bob McMurray and Larissa Samuelson and their student Jessica Horst, who's now at the University of Sussex. But Bob and I decided we might go into cahoots, and we ultimately did. So how do we actually generate a good animal model of language acquisition or the vocabulary expansion? Well, one thing that we have to worry about is the fact that many of the primate projects involve immediate interaction with people. And I'm not so sure why all these projects have that feature to it, but it's an element that I think complicates the story. It means that social interaction and richer opportunities for word referent learning are possible. It also raises the specter of clever Hans errors and the other complications that we would rather do our best to eliminate. Another issue of a model system, though, and more relevant here, is that it should involve many word reference, not just four, and we should also have these reference unfolding. I mean, children's vocabularies increase, right? So what are we doing with just four categories being simultaneously taught? We're not really accumulating a vocabulary in the way that perhaps children do. So we had two different approaches to this problem. The first was a project that Dan Brooks worked on quite some time with us. It trained pigeons to categorize 16 different kinds of objects from the earliest categories that little kids learn. They included baby, bottle, cake, car, cracker, dog, duck, fish, flower, hat, key, pen, phone, plane, shoe, tree. We didn't pick them because we like those in particular. Those were the first ones on the list. Across several studies, these were the most common words that little kids learn. And we wanted to eliminate some of the factors that might have contributed to performance before. So we had now the stimuli rendered in black and white, and we took away background cues. We didn't do as assiduous a job back then as we could and have now since. We, in this experiment, trained with 8 different examples of each category, and we saved 4 more for testing in generalization. And those would be examples of ducks. The training stimuli are on the top, the testing stimuli are on the bottom. Those are flowers, I hope you realize. I can't tell you which ones they are. Those are shoes, some really wild and crazy shoes, I've got to tell you. And planes, all different kinds of planes and all kinds of different orientations. So we were inspired by Kanzi's lexigram board, and we decided we'd create something similar for pigeons, and since they peck, of course, we're going to call them pexagrams. We had these pexagrams very similar to what the others had used before. They're colorful geometric shapes. You'll see some examples in a second. What did we do? How did we proceed? Well, the categories get increasing in number. So we start with 1, and then we add categories progressively up to 16. So 2 of the birds got all the way to 16. Each had its own appropriate pexagram, a token, it's the moral equivalent, if you will, of a word for the particular category that we're showing. And we're going to progressively go through 1 to 2, 2 to 3, 3 to 4, and so forth. We're going to keep expanding the bird's repertoire as we go. We figured, though, that we would give half of the trials to the new category that we introduce. Because if we didn't give more of those, they would never learn. Because as we increase the number of categories, there are only going to be 128 trials in a session with 16 categories. That's not many observations, and not many opportunities to learn. So the other half of the stimuli were divided equally into however many categories they had learned before. So if they were learning 5, right, 1/4 of the others of that half a session would be from the other 4 categories that they had learned. So this is what the full board would look like when complete. So there would be a picture of the duck. This would be the report response for duck. These would be all the other different categories arrayed below and to the side of the stimulus. Once again, now the pigeon pecks the key. When it completes the observing response requirement, the appropriate number of keys come on, depending upon how many categories had previously been learned, and the pigeon has to choose from those. So this doesn't get filled out quickly. It takes a long time before the birds get adept at all these different categories. So you see what's happening? We're just adding categories as we go. Oh, man. So how do we decide what to do next? How do we advance to the next program, right? The next step? Well, the bird, because there's a shifting probability of a correct response with every category that we add, it's a nuisance. We rely on D prime, some non-parametric measure of accuracy. We insist that the new category achieve a D prime of 2.0. But what about the other categories? Well, we have to make sure they're still discriminating the old ones. And to do that, we insist that the mean of all the old ones is also 2.0, and none of the individual categories is less than 1. If you really want to know what the percentage correct is for each of those, I can't tell you because it keeps shifting with the number of categories that you add. But believe me, it's a very conservative test for advancement. And then ultimately we test with novel examples. So all of the 3 pigeons that we studied mastered the first 14 problems. They acquired the problems at similar rates until we hit 10 categories. At that point, 2 of the birds took longer to learn the remaining, and 1, yes, my favorite, 9W, the genius, showed no difference. He just kept right on going. We don't know how much farther he could have gone, but we ran out of space on the board. So this is the number of sessions necessary to reach criterion for the first 2 problems, the next 2, the next 2, the next 2. And then when you see hit 10, we start seeing something happening. And then it takes a lot longer to master the 13th and 14th categories that have now been added. Now there's 14 of those pexagrams are live at that point in time. 9W, what a champ. We also then, of course, had to measure generalization. Had they just memorized the individual exemplars? What happens if we show new examples? And at that point, we did this test after 15 categories. And you'll see now that both of the pigeons learned and generalized. Here are the data. There's 9W. He doesn't actually look very different from 68Y in terms of transfer. But remember, if you're not impressed by 40% correct, you have to realize what chance is at that point. And also you know that the number of examples per category is important. So they were only trained with 8. We know that if we had trained with more, they would have transferred better. But we also know that if we had trained with more, I'd still be running the birds now. So why the hell would I do that? Well, that was a model for how a vocabulary can get bigger. But is it a realistic one? Do children have this assiduous training where they learn one category, then you add one, they learn one and you add one, they learn one and you add one? Maybe not. Maybe they're just bombarded with a whole bunch of categories, and the sequential increase is just the product of their natural learning as different categories come online. So we had to perhaps rethink the way we're going to do the experiment. And Bob McMurray and Dan Brooks worked on this project. Bob was really instrumental in getting this off the ground, largely by telling us what the trick was that was used for human research. The children weren't given one alternative. Well, if they were given a category, they weren't given like 87 different responses that they could conceivably make. They were only given 4. And I said, why not give them just 2? And so we did. We now have a 2-key procedure where the pigeon sees one of these pictures, same pictures from these categories. There's 2 buttons. One of them is the correct one, and one of them is an incorrect one, randomly from the 15 other categories. So now we can train all 16 categories right from the beginning and see how category learning proceeds. We randomize the location of the report buttons now for the first time rather than leaving them in fixed locations. And once again, the pigeons will get 128 trials here. They'll learn and you'll see generalize. So this is what the board looks like now. Whoa, much simpler, right, for us and for the pigeon. Now there's always a 50% chance of being correct. There's not this sliding scale of probability as more categories are added. And as I said before, we randomly locate the correct button and incorrect button on either side. And the incorrect button, to emphasize one more time, is randomly one of the 15 incorrect categories. Of course, a wrong category button on this trial is a correct category button on another trial when the picture for that category shows up. So here was learning in terms of proportion correct. You see another star in their stable. This one's 45W, gets up over 80% correct. The other guys, well, perhaps not so impressive, but certainly the learning was statistically significant. And to give you a different idea about the level of learning, here are the accuracy scores in terms of the percentage of categories that are statistically above chance within the block. So you can see that this bird is hitting 100% to all 16 categories really early, and the others get pretty close to that as well. And perhaps even more impressively, here are the individual birds on all 16 categories, baby, bottle, cake, all the way over to shoe and tree. Remember all those? Right. And every one of these scores is statistically significant, and it's above chance. The birds are reliably discriminating every bird, every category over the course of acquisition. And now the question is, what about generalization? And although the birds do differ in their accuracies, once again 45W is the champ, they all show, well, similar generalization decrement, but they all did learn and they all did generalize. So it's perfectly clear that pigeons can learn to name 15 or 16, what am I talking about? 8 black and white slides from 16 categories by pecking different multicolor pexagrams. The new categories were added by the pigeons in one of 2 different ways, by our successively adding them, or by the pigeons successively adding them. In this case, in the first case, was when we successively expanded the vocabulary by adding buttons and categories, and in this case, by the pigeon doing so, by increasing the number of accurate reports. And in each case, the pigeons transferred to 4 novel photos from the categories. So we think that these data importantly extend our prior research on pigeons' categorization and suggest a role for associative processes in human word learning. In case you wonder, where is this paper? It was just published in Cognition. It isn't one of our normal venues because we didn't want it in one of our normal venues. We wanted to rattle people's cages, right? We wanted to suggest that there are potentially important parallels in how pigeons may acquire a rich categorical repertoire, suggesting that associative learning may be a substrate, an important substrate for even human word learning. Of course, you ask, everybody will, are these deep or superficial resemblances? In the paper, we have a great many more analyses of the pigeon's behavior, as well as lag analyses telling us about perseverative responses based on position, the prior foil, the prior correct alternative, what the picture category had been. Suffice it to say that in there, in the weeds, are some really key parallels to how children learn and the mistakes that they make in vocabulary learning. But we obviously have to do many more experiments to pursue the paradigm, but I think this is a novel approach. And the title was The Evolution of a Paradigm, and you can see how we moved from Herrnstein's, I think, quite simplistic analysis to something much closer to the kinds of issues that will make our work relevant to a broader community. So I have a few points to note to wrap up. This is where I do a little bit of philosophy and theorizing. So the questions that I'll consider here are animals locked in? And must we humans be so arrogant? If you haven't ever seen the diving bell and the butterfly, it's something I think most psych majors should see. It was all a book and a movie. It's about a man who was in a serious car accident and, so far as anybody could tell, was in a vegetative state. Couldn't speak, couldn't move, except that he could blink one eye. And his caretaker saw something and was inspired to try something, and it turns out that he was able to blink at the point where reciting the alphabet, A, B, C, D, E, the letter in the word that he wanted to spell hit. So he would keep blinking until he stopped, and that was the letter. He spelled out the entire book this way, and the movie details this process. So locked in is the syndrome where people can't communicate, but if you give them a means of doing so, they can. And it's always eerie when you hear these stories about somebody regaining consciousness and you just were ready to pull the plug on them, and inside they're yelling, "Stop, stop," but nobody can hear them because they can't speak, like our pigeons. So here's the issue. John Locke said that animals lack the power of abstracting or making general ideas. Remember why? Because they have no use of words or other general signs. But I suggest that we can provide them with general signs. That's what those button presses are all about, and all the other tricks that we use in our science. I suggest that if we provide animals with these signs, what you might call general signs, in this case they were pexagrams representing artificial and natural categories, we might learn much more about their cognitive processes. They may not be the vegetables that some people would like them to be. These general signs can help us appreciate the perceptual and cognitive processes of otherwise silent animals and let us answer questions like, what do they see behind the occluder? Right? If we're clever enough to ask and answer these questions, maybe they'll come through for us. And I suggest these are the general signs that can serve as the moral equivalent of words for these animals. Prepare yourself now, if this works. This means that animals will not be locked in anymore. What are we doing, Olga? I'm not done yet. He was trying to get rid of me already. At least it was after the punchline. Slightly. What about human arrogance? This is something that is a very serious issue for us. As much as people love animals, they also disdain them, and in many ways. So We find when we talk to our cognitive colleagues that we don't always get a warm reception. That somehow insisting that animals may have perceptual and cognitive processes that are similar doesn't go over so well. There's a lot of resistance, a lot of pushback. Why is that? Well, Michel de Montaigne, in his apology for Raymond Sebon, had something to say. This is a name, if you haven't ever looked him up, he has some really provocative and important things to say about animal behavior. Much more modern than Descartes and Locke, much more enlightened, although this is the beginning of the 17th century. He said that presumption is our natural and original infirmity. Of all creatures, we are the most miserable and frail, and yet we are also the most arrogant. That arrogance leads us to ascribe divine attributes to ourselves and to separate ourselves from all other creatures. Now, he was no scientist, but he was an observer of nature and a student of the ancient texts. He noted that communication, animals communicate with one another, they build nests, and they engage in some kinds of reasoning. Those anecdotes from all ancient scholars come to mind. But in any case, he suggested that animals and humans, because of this, may obey the same laws of nature. And therefore, that there is no special place for humans in nature, or part of nature. Starting to sound a lot like Darwin, but way before. And another author had something similar to suggest. And this author is not one usually associated with the science of psychology or psychology or science at all. And his comments I found particularly astute, and it'll give you something to chat about perhaps later over dinner. He said this: though you stand on the top of the ladder of life, you must not kick out that ladder from under your feet. You must not deny your relatives, the other animals. Their history is your history. And if you kick them to the bottom of the abyss, you go yourself. By them, you stand or fall. What you repudiate in them, you repudiate in yourself. A pretty spectacle, truly, of an exalted animal striving to disown the stuff of life out of which it is made, striving by the use of the very reason that was developed by evolution to deny the possession of evolution that developed it. He said, this may be good egotism, but it is not good science. And the surprising author of what I consider to be these really profound and important words was this man, Jack London. And he wrote an essay called The Other Animals. And you might write it down, take a look at it. It's really interesting. He was embroiled in a different debate at the time. Remember he wrote Call of the Wild, he wrote these stories from the perspective of the animal. And then there was this big debate about whether this was really the right way to think about animals. They're just people inside fur, right? I mean, you're attributing all human motives and ambitions and cognitions to the animals when they're not animals. I mean, they're not humans at all. In any case, he got embroiled in this debate, and there's some interesting back and forth in the literature about this. So, I want to thank Jack London, the two Freds, Keller and Skinner, Nat Schoenfeld, Dick Kernstein, all my many collaborators, and all of you for your attention. Thank you. Questions, comments? Yes, Tony. Not Tony. Jerry, the damn hat. You guys wear those hats.
Wonderful talk, Ed. But I'd like your thoughts on where that leaves us with the animal rights people.
You're asking the wrong guy. What the hell kind of a question is that?
Well,
honestly,
you end up with this beautiful statement, which, you know, animals are people in fur.
Well, the fact of the matter is, you all appreciate that the more we know and understand about animal behavior and cognition, the more we see resemblances. Those very resemblances are the things that set people off. I think all we can reasonably do is be respectful of the animals we study, to appreciate, at least from our perspective, that they're contributing to our understanding of them and our respect for them and our efforts to preserve and protect them. And those who would destroy us and our work are actually, those are the hearts of darkness, because we will never really understand animals. And I think to an important degree, understanding animals is to understand ourselves. And if we don't have that understanding, we're losing a lot. And the way the world is going, we have an awful lot yet to lose. But it shouldn't be a downer. I'm inspired as much as ever to understand animals. I talk on the radio. I was on in the biggest contrast in radio interviews in my life. First was BBC World Radio. Next was Pet Talk out of Keokuk, Iowa. The one lasted 5 minutes. The other lasted an hour. Guess which? Yes.
You emphasize one side of the coin, but if you said the more we study, the more we discover similarities. But the other thing is also true. The more we study, say, every pair of species, the more we discover differences, because we know that. So there's no question that if you're going to put, if you respect the very old and uninformed category of humans versus everybody else, you're doing something very stupid, because obviously the differences between a chimp and a Drosophila is much greater than being a human and a chimp. But just to say that the road goes in only one direction, that actually the more you study, the more you aggregate, is misleading. It's only half the story.
Right, and I was responding to Jerry's point. The fact of the matter is that we also appreciate differences, right? And there's no rule that says that the pigeon has to behave as people do. But there could be core principles or processes that we are uncovering. Maybe there really are really vital differences in how the pigeon is learning these categories and how we learn words. We're wide open to that possibility. We're ready to explore it. But people, are going to have to get over some of their own prejudices. Why would it be an insult if associative learning participated in all of our word learning? Why would that be a problem? I don't see it, and I don't think necessarily others do as well. We've already gotten quite a few comments back about the Cognition paper. And, I think that's another point to raise at dinner or at the business meeting, but we have to do a lot more communicating with these people out there. We just can't keep talking to ourselves because there are fewer of us to talk to. So what we need to do is expand our vistas, and if we don't challenge ourselves to do that, we will just, become a very niche enterprise. Well, we already are a niche enterprise, but we would like to expand, right? We would like to build out. And working with the developmental psychologist, a world authority in language learning, doesn't hurt my cred in terms of making these arguments. And that, I think, is another message that's really important. I had worked with Irv Biederman on studying visual perception in pigeons, object recognition, right? The Geon theory. Well, that wasn't an accident, but that community, the vision science community, is not the cognitive science community. They are not the same people. The vision scientists are wide open and accepting for animal research. Wide open. Go to vision science, people flock to our stuff. They love it. Go to cognitive science and see what you get. Ain't the same. It's a different story altogether. Well, we have to appreciate that, but be prepared to have a fight. So the emphasis on commonality is a political one. The reality, the scientific one, is we take the data how they come, and we interpret it as best we can, for sure. Alex, you're exactly right. Yes?
Is there anything interesting about the mistakes that pigeons make on these tests? Like the area that there's some stimuli that are really hard for them to learn?
Yes. Ever since Don, where are you? Raise your hand. Attaboy. Don Blau pioneered the use of errors and the exploitation of errors in our understanding of perception and cognition. And we've done many experiments that look at those errors. But we do have those kinds of confusion matrices. Dan and Bob and I looked at those. I wish that they had proven to be more revealing than they have. The real secret to doing those experiments, Olga, where are you, Olga? Right. I mean, if you build in differential degrees of similarity, then you can go places. Yasu used the 3 response alternatives to look for those confusion errors. Yes, errors are way more important than correct responses in diagnosing process. And we thank Don for really pointing us in that direction. That's the way the field should go. You know, go-no-go experiments, they give you a continuous measure of behavior, all right, but interpreting it is really hard. A more discrete response can sometimes be more revealing. Yeah, Ludwig.
I would like to come back to the beginning where you started with concepts and Bernstein's thinking about concepts and then category. I mean, categorization in the perceptual world is okay, but I mean, if you compare pigeons and humans in the same task with the very same stimuli, like Smith et al. Did, where you can...
Like what?
Smith et al. Did, where you have 2 separate dimensions, and either one is relevant alone, or both are relevant. So the analytical versus the synthetic approach. What is your last word at the moment about that? Is the pigeon less conceptual, less analytical, or is this only a matter of perceptual?
Well, Bob's an author on one of those papers. I've not yet bought into that distinction. I think the stimuli are, if one wants to talk about unnatural, I think that would be the first, that would be exhibit not into that. I think we need to expand outward from those gradings that are different widths and different orientations. I think we would need to look much more assiduously at that. Having been I won't betray any confidences, but having been a reviewer of many of Ashby's experiments, none of them with animals necessarily, there's a lot of pushback, not from us, but from other cognitive psychologists about whether those are really the right dimensions, whether those are the axes of performance. I'd love to know more about that, but at the moment, I'm not so sure. Fabiana and I published a paper in JEP Animal looking at holistic and analytical processing, and you change the nature of the stimuli, you change the nature of the processing. So I think it's probably highly constrained to the particular dimensions and stimuli that they chose, and perhaps not transportable very far beyond that. But I appreciate the question. It's one that does come up. And Bob, where are you, Bob?
I'm right here.
Well, he can fight over this later on with Ludwig. Yes?
This may be highly related, but it seems to me that our categorizations come complete with a definition or a function of the thing that we're categorizing. And it's not just a perceptual categorization. There's more to it. And so I wonder whether or not the categorization you're talking about is what language is.
Well, I don't think I could agree more with what you just said. When I was trying to introduce the other paradigms, you have the name for ball. Well, the chimps got the ball, right? I mean, you play with the ball, you can smell the ball, taste the ball, but Kanzi does with the ball you don't want to know. I was there. It's not a pretty picture. The fact of the matter is that there are all kinds of other accompaniments. Well, we don't have that enrichment here. You say, maybe that takes something away. And I say, exactly. It does take stuff away. It strips it down to its basics. And that's where we want to start, the ground floor. Now, can we build more in? Tom, where's Tom? We have associative concepts. We have ways to embellish and enrich these associations in terms of different outcomes, right? Different locations, different kinds of foods, right? We have other ways to embellish these associations. But we want to start at the most basic level. And yes, back to the issue of occlusion, on the question, the really astute question they asked before, yeah, they're working in a two-dimensional world. I'm going to answer your question, the one that was asked of you. So yes, the pigeon is working in a two-dimensional world. Well, people don't usually work in a two-dimensional world either. They have to learn how to segregate a chaotic environment on a computer screen. But there's a much better example. Kids in India, from birth, have been blinded by cataracts. There's a project out of MIT where surgeons, this one great guy has gone in, done the cataract surgery, and then watched children learn to see. And the first problem they have is separating out the objects in the world. If they come in close contact with one another, it becomes one object, right? They don't segregate them. So they have to learn in a three-dimensional world how to break things apart. So when a bonobo sees a two-dimensional screen, you say, well, bonobos must surely be able to translate what they've learned in the 3D world to the 2D world. Don't bet on it, because it's a different world. And I think these are the basics, the elements of association, of experience that we need to study. We have the upper hand. We can't do these experiments with people, as a rule, unless there's this natural experiment with cataracts, where you're allowed to see, the learning of seeing. I think that's a really exciting set of circumstances. I'm sorry for the children. I'm glad for the research that's been done. But it's really revealing something profound about the role of experience in our behavior. We take seeing for granted, but we had to learn to see. Well, there are many things we learn to do at a very early age. As another aside, 11-month-old children are not infants. They're ready to drive cars by then. What the hell? You know, I mean, you read these things in the literature, and my mind just explodes. They're not. I had them. They're quite capable of doing a lot of stuff when they're that old. Talking about babies and infants when they're that old, ridiculous. We just don't appreciate the richness of learning because the kids aren't talking. It's too soon for their speaking. So, talk about a category. Infants are all those children who don't speak. Right? Anyone else? Bob?
Yeah, I'm no developmental psychologist, but I think if they were here, they would say that it's all really nice stuff, but the one axis you had there at the bottom had 10,000 trials, 20,000 trials, 30,000. That's, 4 months, 8 months, a year to get those 16 words, and we look at our kids and we say, well, they didn't struggle nearly so hard to get those 16 words. They had those in no time at all.
So, of course, it could be the matter of quantity, right? I mean, there may be different speeds of learning. But what you really don't know is how fast learning happens in vocabulary and how many thousands of experiences kids actually have in learning. Bob McMurray, my collaborator, has a science paper about how many thousands of experiences they need. It isn't that small. And the explosion of words is the result of a normal distribution. The easy ones are learned first, the hard ones are learned last, and the middle ones are learned in the middle. And this gives you this false sense of an explosion of a category learning, when in fact it's just the ease of learning particular words, or the number of experiences they may have had. In any case, it's an open question. It's an exciting question, that's why people are studying it, but it's a hard question to study. People don't just give out their kids, oh, here, you do some experimentally naive children, well, we'll just, here's a ticket to the maternity ward. It doesn't work that way. Well, thank you very much for your kind